So, ladies and gentlemen, welcome to the midpoint of the Geology lecture series this year. The third talk this evening. We still have two coming up, and because Carolyn brought too many giveaway things, I don't have enough hands. So if you didn't partake of some of the information that she had available, there's some stuff that may still be available out there a little bit later. Thank you, because I'd rather have this in front of me than your stuff, no offense intended. If you don't have April 2nd circled on your calendar yet, you can go ahead and do that. There are also some posters out there if you would like to take them and post them in various businesses and the like, including apparently the gym that didn't get one last time. April 2nd, we've got Andrew Fountain coming down from Portland State, very widely recognized, actually former employee and former coworker of Carolyn Driedger's, that is at Portland State now, going to talk about glaciers in the Pacific Northwest and the impact of small glacier retreat on sea level change. So the final talk, if you go to www.swocc.edu, you can track it, is going to be June 4th, is going to be a speaker from Penn State. More about that some other day. So it's my great pleasure to say hello to Gold Beach, because we neglected that last time. Hopefully you are out there and can hear us and see us, and anybody else that might be out there in the ether world, and to all of you in front of us as well. It's my pleasure to introduce to you this evening Carolyn Driedger, who's been with the USGS for a couple of years. She's their outreach person, which is very important, because when you start thinking about the number of geologic hazards that we have in the area, whether it's our local earthquake activity that we tend to hear about regularly, or just a few hours into the valley, into the Cascades, getting the word out about what some of those issues and concerns are is probably one of the most important things that either a state survey, or in Carolyn's case, the United States Geological Survey can do, because it keeps us safe and keeps us aware of the things that are going on around us. So it's my pleasure to introduce to you Carolyn Driedger.
Thank you, Ron. I'm so pleased to be here, and thank you to all of you for coming out to on a cool, wet evening, a damp evening in Coos Bay here, coming out to hear about some fiery geologic phenomena in the Cascade Range. So appreciate your coming out, and thank you for making me feel welcomed here. You know, I had a nice dinner that Kathy and Ron prepared at their home this evening, and I heard about your community, and it sounds like a wonderful place to live. So very happy to be a part of it this evening. Thank you. But tonight we're going to talk about volcanoes, which is probably not the first hazard that comes to mind when we think about what happens along the coast of Washington and Oregon, Northern California. Probably the first thing we think of is earthquakes, right? And tsunamis, and I think that you've heard a lot about that over the years, and very rightly so. And it's the same phenomena. That subducting slab, that piece of oceanic plate that is sinking beneath North America, it's that same piece of rock that is causing havoc in the Cascade Range too, and which has produced the beautiful volcanoes that we see today. So we're going to take a little bit of a tour. We're going to talk about a variety of aspects of volcanoes in the Cascade Range this evening, and I'll tell you a little bit more about where I'm coming from and why I'm here doing this. And then we'll talk about some of the processes that happen at Cascade volcanoes. And then we'll focus in a little bit on Oregon and look at what you have here in the Cascades of Oregon. And then we'll talk a little bit about what we're doing with the U.S. Geological Survey and its partners in emergency management are doing to help prepare people for the next eruption in the Cascades. And yes, I can tell you right off the top of my head, right now, right off the top of the talk, that we don't have any volcanoes that are overdue or threatening to erupt right now. Are we happy about that? And certainly none that when they do erupt are going to bring any kind of a significant hazard to Coos Bay, but some of our friends and family up and down the Interstate 5 corridor and through the state of Oregon and Washington will certainly be affected, and that may affect you here in Coos Bay as well. So let's start off. I mentioned I wanted to say where I'm coming from with all this. My background is actually in studying glaciers and glaciers on volcanoes. And I was fortunate, I guess, in 1980 to be a young geologist, just joined the Geological Survey. But my interest was in studying the glaciers up on Mount Rainier. A colleague said, you know, at Mount St Helens, we have an interesting situation. We have a glacier that moves relatively rapidly, and we know there's a lot of water flowing underneath it because we have a lot of heat from this volcano going through unrest, Mount St Helens. And she said, let's go. I'm going to work on that on a project. So I went down to Mount St Helens, and she took a number of people with her to help on her project. And the time she asked me was for the 17th of May, 1980. Didn't seem very auspicious at the time, but you know, when you're young and you are completely, you're fearless. And so I thought nothing of driving with her up to Coldwater 2 at Mount St. Helens and delivering some equipment from our glaciology office to our volcano brothers in science. They needed a distance measuring device to measure the distance to the growing lava bulge on the north side of the volcano. And so we decided to stay overnight because the helicopter was going to be delayed in getting to us to take us to our work site. So we took our sleeping bags and tents out of the car, and the geologist on site at the time, David Johnston, said to us, you know, this is not the safest place to be. I think we should put as few people here at risk as possible. And so we talked for another hour or so, and then Mindy Brugman, Harry Glicken, and myself left Dave behind, and Dave said he needed to be there, but he'd be okay, and we'd see him in the morning. So, of course, we went back to Vancouver somewhat dejected, and in the morning we were driving back up to Mount St. Helens when we watched the north side of the mountain disappear towards the north, and soon recognized that Dave was a part of that very unfortunate circumstance. And so Dave, of course, was killed during the eruption. But at that point, we didn't have any cell phones. We drove up to Woodland and found a coin phone and called back to headquarters, and we said, what's happening at Mount St. Helens? This looks very strange, not like what we've seen before. And they said, come back and start answering telephones. And so within half an hour, we were back there talking to the media, trying to understand and trying to inform others of what was going on, trying to listen to people in the field tell us what was going on in their neck of the woods, trying to digest all that had happened to our colleague. It was a bit of a kind of a frightful day, actually. But it did convince me that we probably needed to do, the USGS and scientists in general needed to do more work with public officials, the public at risk especially, and emergency managers preparing for the next eruption in the Cascades. Right, and then I went on to work on glaciers on volcanoes and looking at the amounts of ice we had on them and looking at debris flows at volcanoes. And then in 1990, I came to the Cascades Volcano Observatory. So just so that there's no confusion, we're in Vancouver, Washington, Vancouver, USA. They keep threatening to rename the town, the Couve or whatever, Fort Vancouver, but we're in Washington State. And there you see a picture of it in 2004 when we had a lot of media trucks out front when we had an eruption going on here at Mount St. Helens. So since about 1995, I've been working mostly in outreach, public outreach, reaching out to policymakers, emergency managers, emergency planners, land use managers, other public officials, as well as professional information distributors, such as the media, working with teachers, park interpreters, and such, helping them get the message out so they can give the proper message to people at risk. All right, so what is it like to be in the presence of an erupting volcano? Raise your hand if you've actually seen an erupting volcano. Anybody actually been in the presence of one? It's pretty awe-inspiring, isn't it? A very primitive, somewhat primeval experience. You may experience fountains of lava or lava moving over the Earth's surface and cooling rapidly. It may be very dramatic. There may be snow and ice involved, as there often is here in the Cascades. But the point is that in the United States, all these types of volcanic events have happened in our history. So we are not alone. We are not the first to encounter, to have a volcanic threat in our backyard, so to say. So let's listen to a few voices of people who have experienced these eruptions in the past. At Mount Baker, up by the Canadian border, the native people noted that all the fish in the Skagit River died, probably because of a lahar, that is volcanic mud flow that moved downriver. A tremendous convulsion took place, changing the whole aspect of the mountain. And that was probably referring to the opening of Sherman Crater on the volcano's southeast flanks. Mount St. Helens in the 1840s, the Goat Rocks erupted on the north side of Mount St. Helens. Ash fell in Fort Vancouver and in the Dalles, and that was reported by fur traders. At Mount Rainier, the native people have a variety of legends. Well, they're called legends, but I tend to think that they are true stories, actually, of how Tacobid, the native name for Mount Rainier, Tacobid's head broke open, and the lake on top spilled, and the water rushed down. It filled the place where Ording now is, and left the prairie covered with bubble-filled stones, as in scoria and pumice. So we also know that there are a variety of places where volcanic ash covers spear points and obsidian flakes and such, and moccasins, such as at Crater Lake National Park. We know that ancient peoples were here, experienced eruptions many times, and tried to make sense of it as best that they could. All right, well, so one of the things I'd like to say is that at these Cascade volcanoes, change is a constant. We have continual change going on. And so, we can look at the people who were here back in the 1890s, this Faye Fuller here at Mount Rainier, and here's some dancers back in the 1930s. They were posing for a car company ad. And some little girls here back in about the 2000. And so, what all have they experienced? Have they experienced change? Undoubtedly. And I like to say that from these stories, we can be assured that the mountain that you see, the view that you see of these volcanoes is a little bit different from what your grandparents saw and what your grandchildren will see. And if you think back on some of your visits to Crater Lake or volcanoes in the Bend area, I think you'll recognize that some changes have happened there, even maybe just to the glaciers, but certainly with the rocks as well. Plate tectonics is in the Ring of Fire. Where are we on it? Well, let's just get situated geologically. Here we are on the Ring of Fire. Here's the Cascades, and you know that the Earth's surface is broken up into large plates that move around a little bit like graham crackers on frosting. You can move them around a little bit, and they do various different actions. Now, for example, here's the San Andreas Fault shown in black here. You can see that it's sliding north. Here's the Bay Area. Goes out to sea at Cape Mendocino. There's San Francisco. And then we have these areas where these are actually spreading centers where we have rock moving towards North America and moving away from North America as well, both directions. And they are connected by fault zones as well. We call them transform faults. And then north of Vancouver Island, we have a very long fault zone. Here you can see the direction. We have the rock moving. It's actually more dense than the rock of North America, so the rock of the ocean bed is sinking to the east and beneath North America. All right, and then we have a Cascade volcanic arc, as we call it. But in addition, we have some other volcanism in the Pacific Northwest. Maybe it's stretching the term a little bit, but we have Yellowstone caldera, which we're actually seeing the path of North America over a hot spot, if that hot spot is indeed staying intact. And it has caused a whole train of different volcanic features along this path, 1,000-mile-long path or so. Okay, and then down here in Oregon and Nevada, we actually have the land pulling apart and causing small volcanoes to form in southern Oregon, eastern Oregon, and in Nevada and eastern California. Okay, so the result of all this movement of rock is that we have volcanoes formed in somewhat of a roughly parallel pattern, parallel to this rock that's sliding beneath North America. And it's 1,000-mile long, over 1,000-mile long chain of volcanoes. This stretches from, actually, it's probably more like central British Columbia down to Cape Mendocino area, Lassen Peak in Northern California. Well, let's take a look at Washington's backyard volcanoes, and then we'll go over Oregon's backyard volcanoes, as I like to call them, real quickly, just to refamiliarize yourself. By the way, here is Cascades Volcano Observatory. You may think that it's in somewhat of an unusual, out-of-the-way place, but we're halfway down the Cascade Range, so within a day's drive, we can get to all the volcanoes north and south of us. But about just a few miles south of the Canadian border, 20 miles or so, we have Mount Baker, beautiful volcano, which erupted in the 1840s. I'll show more of the eruptive history later. And then east of Everett, Washington, Glacier Peak. Mount Rainier, probably one of the most famous of the Cascade volcanoes, one of the largest. Mount St Helens, probably the most frequent erupter during the last 4,000 years. Mount Adams, which is actually by volume the largest of the Cascade volcanoes, hasn't done much recently. And then in Washington, we actually claim Mount Hood, Oregon as well, because there are hazards that stretch into Washington state. We also have what we call the boring volcanoes, which are very small cinder cone type volcanoes in the city of Portland itself and into Clark County and around Vancouver. And then of course we have Columbia River basalts. This is a large outpouring of lava that happened between about 14 and 16 million years ago. So, hey, we're really living the volcanoes, aren't we? There's a lot of volcanism in our area in the Northwest. Going to Oregon, here's Mount Hood up by the east of Portland. Followed by Mount Jefferson, maybe a little bit different view. This is a close-up view that shows some of those little peaks that you may not recognize from a distance. The Three Sisters volcanic complex near Bend, Newberry Crater, and Crater Lake. So these are the principal volcanoes, but I'll mention in addition that we have hundreds of small volcanoes in the eastern Oregon area, Bend, Redmond, that region. And probably only erupt once and then go to sleep forever. Okay, so let's look at some of these major volcanic peaks and understand a little bit about when they erupted. You know, the USGS has as its mission to determine when these volcanoes have erupted in the past, because we know that what's happened in the past is a key to future eruptions in terms of style and timing. And so we've made this graphic, which I've been impressed, even a lot of little kids understand. So I've showed it to third graders, they get it right away. They've done timelines in school. So here's a map of volcanoes. Here's a timeline from 4,000 years ago, arbitrarily chosen, to the present. And this red dashed line indicates the time roughly when our nation was founded. Each of these little volcanoes indicates a volcanic eruption. So notice that we have had not one or two, but 1, 2, 3, 4, 5, 6, 7 Cascade volcanoes that have erupted since our country was founded. Now that's roughly 1 or 2 eruptions per century, and it's one for almost every generation of Pacific Northwesterners or Northern Californians. So that's just proof of how this is an active volcanic range that we can expect will erupt again. You can see that Mount Baker erupted in the 19th century, mid-19th century. Glacier Peak numerous times. Mount Rainier, Mount St. Helens have been frequent erupters. Not so much with Mount Adams, but certainly the Three Sisters has been active. And going down to Mount Shasta, you see it has been one of the more active volcanoes as well. And notice that in Washington State, we tend to have more volcanoes erupting during this particular window of time than in Oregon. And we talked about that and decided that it's pretty much an artifact of the little time window that we've shown in this graphic, because we have had many eruptions a little bit more than 4,000 years ago in Oregon. Right, and of course some of you saw this on the poster. You can take a copy of this home with you. So these Cascade volcanoes, I like to call them functional volcanoes. You know, the question comes up, do we call them, are they dormant volcanoes because they're not spouting out right now, or are they active volcanoes because process-wise there is earthquakes going on? We have hydrothermal systems that are active. They've had recent eruptions. They're producing new magma. We can see it under the volcanoes. So I just like to call them functioning volcanoes, and they're doing what volcanoes do right now. They rest for a long time. They're like cats, right? They rest for a long time, and then all of a sudden they get up and they do a lot of activity, and then they go back to sleep again, and then they wake up, etc. And just like your family of cats, there is no set time period between when these different volcanoes erupt or when they get active. So we don't know when the next eruption is going to be, and I'll tell you right now, after spending a lot of money on it, we can tell you that we cannot predict when the next volcano will go into a period of volcanic unrest. But once one does, once we see the clues and we know what to look for, then we can give a better idea of how soon it will be until the eruption happens, and a little bit better idea of what kind of eruption will occur as well. Okay, so now the Cascades have, they're a little bit more complicated than a lot of volcanoes because they have these beautiful snowpacks on them. It makes the volcanoes really lovely, doesn't it? You see Mount Shasta, Mount Hood, Mount Rainier, for example. This is Mount Baker in the picture. And it's an extraordinary amount of snow and ice. And back in the 1980s, after Mount St Helens erupted, some of us carried radar gear around these volcanoes, and we measured how much snow and ice was there. And we found that Mount Rainier, by far, also the volcano that's closest to major population centers, has the largest amount of snow and ice. In fact, there's about 1 cubic mile of snow and ice on Mount Rainier. So if you have a hard time thinking about what 1 cubic mile looks like, just think of an ice cube 1 mile on a side, or you could think of an ice cream scoop. So say you have an ice cream scoop with a Safe Coast Stadium, big stadium in Seattle. You put that on the end of the ice cream scoop, you go over to Mount Rainier to remove all the glacial ice and all the perennial snow, that snow that remains from year to year. You need to go back 2,600 times to remove all that snow and ice off the volcano. And of course, it doesn't take a lot of imagination to think what happens when we have hot eruptive products coming in contact with snow and ice. We have a lot of meltwater generated, and when we have meltwater, we have mud flows forming. We call them Lahars. So this is a very common sequence of events at Cascade Volcanoes. We'll have the melting of snow and ice causing volcanic mud flows, Lahars, that travel down the river valleys to areas distant from the volcano, 20, 30, 40, 50 plus miles away from the volcano. And that is the principal risk at the Cascade Volcanoes. Lahars, that is volcanic mud flows, are the principal hazard from these Cascade Volcanoes. Okay, so let's talk about the USGS and what we do, what our jobs are, what we do routinely. We basically have a pretty much a sedentary office life for much of the year. And then in the summer, there's a lot of frenetic activity, people going out in the field and digging in the rocks and digging in the dirt and trying to understand if they, what eruptions have happened when and what style of eruption occurred in the past. But pretty much we're sedentary at this time of year. Okay, so we make investigations to understand the hazards. We do research to understand what makes volcanoes go pop. We monitor volcanoes. We set out a lot of equipment, have a big program plan for Newberry Crater area this year. And then we communicate that volcano hazard information to people. So one of the research tools we use is a large 300-foot high flume that is east of Springfield, Oregon, in the H.J. Andrews Experimental Forest. And we can make lahars, make them and understand more about how they form by using this device. This is a picture up at Mount Rainier setting up monitoring equipment summer, I guess about 3 summers ago. And then we also work with the park staff and emergency managers, making sure that everybody understands what the issues are. There's a lot required. Emergency managers like to say that a crisis is a poor time to be shaking hands. And we agree with that, that we want to, the scientists, emergency managers, want to build a trust with one another before the crisis happens, because we know it may be only a matter of days after the initial unrest before the actual eruption happens. Okay, so then we fly into action when we do have an eruption like in 2004. We increase our monitoring, so we put out a lot more monitoring equipment, seismographs and deformation, GPS devices and such. We make scientific observations. during the unrest, or during the eruption. And then we communicate. We do a lot of communicating with the emergency managers. Very commonly, I only have a 1 or 2 media groups calling my office per week. But imagine what happens when you get 80 to 100 calling you every day asking for volcano information. So we work with the emergency managers to put together a joint information center where we can get our information out efficiently. Here's the media. You can see all the media trucks set up at Mount St. Helens. It looks like they're all, kind of looks like a, you have to wonder if it's like they're looking at the volcano and worshiping or something. I don't know. But anyway, there's a lot of information exchange required at these volcanoes. Fortunately, they do give us the warning signs. You can't have magma rise into a volcano without causing some ruckus. And we know what those signs are, and we know how to evaluate it. First of all, we look for increased earthquake activity. And I say increase because do you know that we have seismic swarms at these volcanoes frequently? At Mount Baker, at Glacier Peak, Mount Rainier, Mount Hood, Lassen Peak. They all give us a little bit of a fright 1 or 2 times a year. And we know that in 2004, when our eruption began, that it all began with a little seismic swarm that just kind of kept on going. So we take them very seriously. We have people on staff 24/7 watching. If we have total energy exceeding a certain amount, then a beeper goes off and someone goes to their computer and checks it. And it's always really interesting to be in the seismic room during an eruption. There's always lots of discussion going on and people making their best estimates as to what's going to happen next. This is setting up equipment at Mount Rainier a few years ago on the west side, and there you can see there's a little seismometer right in there. It's being put into the ground. All right, we also look at surface deformation of a volcano and the surrounding areas. And did you know that when we have magma rising beneath the volcano, it lifts the volcano slightly. It may lift it by only a fraction of an inch, which is entirely measurable, but it also lifts the surrounding terrain. So even in Vancouver, Washington, 40 miles distant from Mount St. Helens in 2004, we had a bit of the ground being lifted beneath our feet. So these devices, these GPS devices are very sensitive, and we can see that deformation happening. This came in handy in about 1998. We actually were trying a new tool. It's called interferometry, and it's a satellite-based method that allows a satellite to look at the distance between the satellite and the ground surface, and then to make repeated overflies, and then to determine how the distance has changed through time. And from it, we notice that there's an area west of Middle and South Sister. It's called the Husband, and that area actually had magma intruding into it miles below the surface. But it went on and raised the surface of the ground several years for about an inch each year. That started in 1998, and it is that rate of inflation is decaying, so it's not as much as it was before. But probably for 10 years or so, we had magma intruding underneath the ground into the Earth's crust. And you think, oh, well, that's kind of amazing, but then you realize that we have to get the magma into the Earth's crust somehow or another. It may sit there and it may be there forever and cool. It could erupt out of the ground next week. It could be 100 years from now. It could be 500 years from now. But you have to have the magma in place before you can have an eruption. Okay, we also look at the changes in gas flux. Understand that when magma rises beneath the volcano, it shakes the rocks, it forces them out of the way, deforming the surface. But it also allows a lot of gases, CO2 and SO2, to rise to the surface. And we're able to measure the change in gas flux. Mostly in the air. We usually use this device in a helicopter. Sometimes we work on the ground as well. Sometimes we work in other ways as well, with a bathymetry studies at Crater Lake, for example. We're able to see what the volcano looked like and understand more about its history, and that after the big eruption 7,700 years ago, we actually had some small volcanoes form inside the caldera. Of course, we had Wizard Island, which was the only one that punctured the surface. All right, now I'd like to take a look at some of the processes that happen on these volcanoes and I'd like to show you some video clips so you can get an idea of what these processes look like. Maybe the next time you see a volcanic eruption shown on the TV screen, you can identify some of these, and it makes it all a little bit less mysterious, too, to understand what the processes are and how they work together. So just looking at this diagram quickly, we can see that we usually have an eruption cloud. We have a lot of gases coming out of the volcano in the magma early on, and they escape first. And by the way, there is some small percentage of water within the magma, and it's the expansion of that water which drives the magma up towards the surface and thus energizes the eruption. In fact, it can propel, the expansion of bubbles of water can propel hot rock, hot gases up into the atmosphere many thousands of feet. So we have gases rising. We also have volcanic ash falling back to the volcano. Sometimes we get big chunks tossed from the volcano. We have lava flows happening. Sometimes the lava flows break apart and make an avalanche of hot rock and gas. We call it pyroclastic flow. So let's take a look at those in a little bit more detail. First, looking at volcanic gas, I just concentrate on the CO2 input in this particular slide. But a lot of people say, well, you know, I'm afraid that when we have an eruption, there's going to be a lot of gas that works its way away from the volcano and may be hazardous. And understand that it's only when gases are trapped in a tight space, a confined space, that's where they tend to be a problem. But most of the time, they just go into the atmosphere. How does it affect Earth's atmosphere? Is it changing it? Is it changing our climate? Well, let's take a look at some numbers for comparison. You can see that the global output of CO2 every year is about 200 million tons per year. Mount Pinatubo, probably the largest eruption in the 20th century, put out about 42 million tons that year. 1980, Mount St Helens put out about 10 million tons. And by the way, humans put out about 36,000 million tons per year for comparison. So you can see that while volcanoes do pump a lot of CO2 into the atmosphere during an eruption, they do it for a relatively short period of time. Okay, let's take a look at what happened in October 1st, 2004. This is John Pallister of our office, just happened to be up in a helicopter with a thermal infrared camera and was able to take pictures of the very beginning of an eruption. And you can see that there's a lot of steam and water coming out of the ground, a lot of rock in this black section. In the days before this time, there was this area that was of the glacier that had melted, and there was this beautiful blue, clear water in it, and we called it the hot tub. Of course, no one dared use it as such. But the hot tub disappeared when the eruption began, and so you can see the eruption, relatively small event, just going up a matter of maybe 12, 15, 18,000 feet. And you can see it's pumping out of the ground there. So that's how we get volcanic ash into the atmosphere. You can see it's very fine-grained. It can be very fine-grained at distance from the volcano. The volcanic ash is carried by the wind. And so it's the fine-grained stuff that gets a great distance from the volcano. Yeah, here's Yakima. It's for sale. Don't be fooled by substitutes. Somebody had a sense of humor. The larger pieces fall back close to the volcano. So while it may be talcum powder-sized ash in Yakima, next to the volcano on the flanks, you're going to find big pieces and sand-sized pieces nearby. So volcanic ash, what is it? Do we need to be concerned about it? Well, yes and no. First of all, there's nothing mysterious, chemically mysterious about volcanic ash. It's simply tiny fragments of volcanic rock that have been blasted apart by volcanic gases. And so, you know, it'll destroy your boots, destroy your camera, but it's not going to be noxious to you. Second, it falls, very important, it falls at normal temperature at distance from the volcano. So it's not going to fall, you know, in Coos Bay, for example, and cause any forest fires. It does it irritates the eyes and makes breathing difficult. So if you are a person who has breathing difficulties already and maybe requires the use of extra oxygen, you probably want to stay inside and have extra oxygen ready. It's non-poisonous to touch. So the best thing to do if you think you're going to be moving in an area that has volcanic ash in the air is to have a little paint mask. You can use those. Try to stay inside, try to stay away from it just because it's so gritty. It's like dirt falling out of the air. So try to keep it out of your house by putting towels around the doors and windows. Try to keep it out of your computers, and you're going to be fine. Now, the next thing to know is that volcanic ash and aircraft don't do well together. It's a bad combination. Because remember, it's just pieces of shattered rock. And that rock melts at approximately the same temperature that we find in the engines of jet aircraft. So when a jet aircraft travels through volcanic ash, it's ingested in the engine. The ash melts on the turbine blades and causes them to turn unevenly, and thus they have to turn the engines off or else the engine will blow itself apart. And when the engines are turned off, the plane begins to descend, and that's trouble. This has happened 80 to 100 times during the last 20 years or so. Fortunately, airline pilots know what to do. They know to go to a lower altitude. They may have to go down to 10,000, 15,000 feet. At that part of the atmosphere, the air is more dense, and they can start to turn on the engines and kick off that gunk off of their engine turbine blades and get going. There have been no fatalities, but we're seriously concerned about this. Oh, by the way, we've been working on this in the USGS for quite a few years, and it wasn't until Eyjafjallajökull volcano, that eruption in Iceland this past April, that a lot of people stood up and took notice. Okay. Just for some scale, you can see that we've had some enormous ash falls over the United States, and one of them is from your very own Crater Lake volcano, Mount Mazama, back about actually 7,700 years ago. We had a large eruption, very large eruption, we know that. It blew the mountain apart, in large part, and you can see that the ash is visible through British Columbia, Alberta, over much of Nevada, Idaho, etc. And certainly on the slopes of Mount Rainier, where I do a fair amount of work, I can find the Mount Mazama layer very easily. It's kind of orange in color very often. But you can see there have been some larger eruptions as well. Okay, lava flows. Well, they destroy everything in their path. Not very easy to get away from that. You can work with fire hoses and the dikes and try to divert that lava, but it's difficult to do. People have tried it, but the biggest hazard is that it melts a lot of snow and ice, but not as much as the next thing we're going to talk about. It just generally collapses. These lava flows tend to, on the steep slopes, generally tend to disintegrate and break apart. And when they do, they make the avalanches I'll talk about in a moment. Okay, so not all lava flows are as you might expect. This is less of flow and more of toothpaste squeezing out of a tube. You can see from 2004 to 2006, here's the lava. Oh, look at those gorgeous spines and teeth rising in the sky and decompressing and falling apart. Look like big teeth coming out of a gum. And they just roll over very slowly over a matter of weeks, fall apart, and now it's just a big rock debris pile there. So I just wanted to show you that because that lava dome growth is a very common way for lava to come out of the ground here in the Cascades at Mount St Helens, Mount Hood, Mount Jefferson. The lava is very stiff and very viscous, and thus it doesn't flow like you see like they show in all the movies. All right, so again, when lots of times lava domes fall apart, and as they do, they make these avalanches of hot rock and gas, the pyroclastic flows, and this is what melts the snow and ice. There's a lot of mechanical turbulence and a pyroclastic flow, and so it can rip up snow and ice and cause mud flows to form. This is the pyroclastic flow that happened at Mount Unzen in Japan in 1991. You can see there's a little village here. I think I'm sure it's been evacuated. And you can see it's no match to a pyroclastic flow, hot rock of 1,000 degrees or so, Fahrenheit or so. So you want to stay away from pyroclastic flows. Actually, there is a threat from pyroclastic flows at most of the volcanoes in Oregon, but the good news is that it's a very localized threat, principally right on the flanks of the volcano. And now we get to the granddaddy, the Lahars, this principal hazard. By the way, the word Lahar is an Indonesian word. And because we have so many Lahars and Merapi volcano and others in Indonesia, the entire volcanological community has pretty much adopted that term for these volcanic mud flows. So probably the biggest one that really inspired our office to do more outreach, to get out and work with public officials, to try to get a better understanding of the conditions that cause Lahars, was this event that happened in 1985. There's a town called Armero. It's about 40 miles away from not a large volcano, a volcano with a relatively small snow and ice cap, Nevado del Ruiz. But unfortunately, there was a small eruption which melted that snow and ice, and a lahar was headed downstream. There were some reports that there might be a problem, but it was nighttime. There was a big soccer match going on. It was raining, as I say, late at night. And so people tended to turn the other cheek or turn the other way and not pay attention. And as a result, the lahar came through town and it inundated the entire town. And about 23,000 people were killed in Armero and in surrounding villages. So this was a huge loss. This was 1985. How many people remember reading about it in the news? Maybe a few. Okay, so it didn't make the big time news, but it was a huge loss for people of Colombia, and it was a huge learning experience for us as scientists. So we've redoubled our efforts getting to areas, working with volcanologists in other countries. We have an international program which goes in and helps people set up equipment, etc. Take a look at this. This is Mount Hood. This is from an eruption. Okay, first of all, this is just mud. First, you can know that the biggest threat from these volcanoes is not fire. There's nothing burning. It's not lava flows. The biggest threat is mud coming into town. So this is not far from Gresham, Oregon, Troutdale, Oregon. Look at these trees that were killed in 1790 by a mud flow coming through. The mud flow came all the way down from Mount Hood out to the Columbia River, went most of the way across the river, buried forest. Lewis and Clark came through, were amazed with what they saw 15 years later. Okay, here's a lahar coming from Samaru volcano.
Tu peux te pousser et monter un tout petit peu, s'il te plaît?
I always think he's a little bit crazy, maybe a little bit jaded, getting so close to these events, but see, this is probably 10 to 15 feet high. And Dallas and those upstairs there, I bet you can hear it on the computer, and it's a rush and a crush sound. Soupy slurry, isn't it? Like wet concrete. Okay, now you know what a lahar looks like. Anxious to see one of those? Here's another one. This one's over in China, but it's not technically a lahar, but it's a debris flow, mud flow that's not happening on a volcano. But I think it gives you an idea of how they move and what they look like. Notice how it hits the sidewall and picks up more rock on the way.
Pretty good size.
It's actually a wire that has instrumentation hanging on it.
Somebody's getting in my way here. Not bad at all.
So you get the idea. These are powerful forces, and you need to get out of the way of Lahars, and you need to get people out of the way when there's a threat of a Lahar. They can travel very quickly, 20, 30 miles per hour, very quickly or very easily, and we know that they've caused a lot of infilling of lower valley floors, like here, for example, for those who are somewhat familiar with the southern Puget Sound area, here is Tacoma, Seattle's up here. Renton, Kent, this is a big valley, but before, about 5,700 years ago, that was actually one of the inlets of Puget Sound. Now we have Boeing and PACCAR and lots of other big companies in the valley. But notice all the sediment that came downstream from a big event called the Osceola mud flow 5,700 years ago. It filled in this area in large part, and it took years and probably decades or centuries for that to happen. But now we're living on it. Okay, and I just want to point out that we can have small events even during non-eruptive times. We can have small debris flows. This is Mount Jefferson once again. Notice the big gully that was formed by all the erosive force of a lahar coming through. Here's a lot of trees that have been stacked up. And take a look at the force of one tree and of rocks against another. There's a lot of serious impact forces here, which will destroy whatever's in its path. All right, so now that we know all about these processes, you've been through Volcano Processes 101, let's take a look at some of Oregon's volcanoes really quickly and just a few aspects about them. First of all, this is Mount Hood, and you can see that there is a little peak up here. That is a lava dome. That's where lava was extruding out of the ground like toothpaste from a tube, and then as it did, pieces of it would tumble down and make a nice, it made a nice flat, or not flat, it made a nice slope here all the way down to Timberline Lodge government camp, Highway 26. And when this happened around 1800, we had trees growing here that were killed by the, perhaps by the pyroclastic flows. It didn't quite make it all the way over, or only destroyed them in part. So we have a ghost forest on the south side of Mount Hood caused by that eruption around 1800. All right, in fact, Lewis and Clark noted that they were coming down the river in 1805, and they found a lot of quicksand, and they were amazed. They said they needed to move their boats to the north side of the river because there was so much quicksand that had come down a tributary stream into the Columbia. They said, I attempted to wade this stream, and to my astonishment, found the bottom composed of coarse sand, which is thrown out of this quicksand river. So they noticed what was going on. Let's look at Mount Hood. The eruption style is to have lava domes that grow and then they fail as pyroclastic flows, and then we have lahars in the rivers. The most recent eruption was around 1790 to 1800 with a lot of steam explosions happening mid-century. The areas at risk are the flanks of the volcano, the ski area, of course, Timberline Lodge, and the river valleys all the way down to the Columbia. And that's going to be a problem when we have hydropower generation plants and barge services put out of commission because of the lahars moving into the rivers. Here's Mount Jefferson again. There's one native story about a great flood that occurred, and the people got into a canoe, and after the flood, the canoe remained on the summit, and people climbed down. I'm not sure what that's referring to. I can say that, again, this is a channel where we did have a big lahar, and floods come through. But the point is, Mount Jefferson has the same style of growth. Lava grows, lava domes grow, that very sticky, viscous lava grows, and then it fails as a pyroclastic flow. Lahars and floods happen, and the most recent eruption was about 15,000 years ago. So it's basically only the areas locally that are affected, except for volcanic ash, distally, away in great distance, and the lahars and the river valleys. Three Sisters, when I put this nice profile up at the top here, my husband assembled. The Three Sisters story talks about an eruption that dropped hot rocks on villages and buried them. Interesting native report. And then the eruption style, we have actually a number of different things going on in a really complicated volcanic landscape in the Bend area. We have the North Sister being of a completely different type of lava, more basaltic, lots of basaltic runny lava, as opposed to the Middle and South Sister, which are more more silicic, have a lot of continental rocks within them. So South Sister erupted about 2,000 years ago, and of course we had all the deformation around the husband of 1998 to maybe to the present. Areas at risk, the flanks of the volcano, and yes, the river valleys in the Bend area have a threat from Lahars, moving through Bend and Redmond Sisters area. Newberry Crater, relatively complicated landscape once again, but basically lava flows. The principal eruptive hazard, last it erupted about 1,000 years ago. But again, we could have lava flows come into Bend from Newberry Crater, and we could have a lot of ash blown to great distance all the way across the northwest. So this is Mount Washington and one of these wonderful, beautiful, exotic-looking lava flows at Mackenzie Pass. Just love that area. Now recognize that this used to be a much larger volcano, but we had an ice age, and with a lot of ice flowing through here, most of the soft material was stripped away and left only the central core of the volcano. So a lot of these happened, a little more than 1,000 years ago, 1,500 years ago. But lots of erosion has made these three-finger jack and Mount Washington, for example, into these very skinny stubs of volcanoes. Then we have Crater Lake. Lots of interesting stories here, but one of the interesting things I found was that there was a story of the Indian who journeyed into the fearful depths of the crater when the crater was still dry. And on the crater floor, there were fissures and mounds and huge gnarled rocks and a strange substance that resembled gold. Probably smelled like sulfur. So, interesting thing about Mount Mazama, Crater Lake, is that this is the source of the largest eruption in the continental United States, larger than any other in the Cascades. So what are we at risk from? Well, volcanic ash, large ballistic rocks maybe being tossed out of the lake, lava flows and pyroclastic surges, a lot of hot material rising in the air and falling over the edge of the crater. Last eruption was like around 5,000 years ago, 4,800 I guess. And so the area within the park is certainly at risk. And certainly if we have more volcanic ash, we could have people affected at great distance. We have some very simplified maps. We also have very complicated horse blanket sized maps that we distribute and work with emergency managers we're working on a series of very simplified maps. I just wanted to show you these ones that are in preparation. See, the area in red is the area that we expect lava flows and pyroclastic flows, but look at these long tendrils. All these river valleys are at risk from the Lahars. Same thing with Mount Jefferson. We could have Lahars down to the west as well as to the east. Newberry Crater the same way. So notice Three Sisters down the Mackenzie River Valley, and then on Crater Lake going down the west side of the volcano as well as the northeast. So these volcanoes offer a threat from Lahars, and Lahars, you may think, well, they're not going to affect us in Coos Bay, and at the same time, if you use Interstate 5, if you use railroad bridge, if you use materials that come up from California, for example, on railroad bridges, or maybe not you as much as people further north, those transportation corridors can be disrupted by Lahars. So the good news is, again, that none of the Cascade volcanoes are showing signs of volcanic unrest. But when we have some kind of unrest, we go to work very quickly, and we work with public officials and the media to tell them what's going on, what we see going on. And We just finished a media guide for Washington volcanoes. We're considering that for Oregon volcanoes as well, training the media so that they can give you accurate information. They can understand what a pyroclastic flow is if we discuss it. We may not have time to train them when an eruption is in progress. So first of all, we try to concentrate our efforts in preparation for communities in the areas where we have the highest risk. That tends to be Mount Rainier, the urban areas, Mount Rainier, Mount Hood, Mount Baker, actually Mount Shasta as well, which I haven't focused on here. Second thing is that the science, we do the science first of all, and then we write a hazard assessment. And I have some assessments out in the lobby. If anyone wants to chat afterwards, I'll be happy to show them to you. And from a hazard assessment, we take these into communities to emergency managers. We start a little, what we call a volcano hazard work group, and we talk about what we have to do to be ready for an eruption. And then we put together collaboratively what we call a coordination plan. And then we practice that plan and make sure that we know whose role is what during an actual eruption. And then we do collaborative outreach in communities as well, going to community events, giving talks, working in schools, working with park interpreters, making sure they get a correct message out. Because when it happens really fast. With Mount St Helens in 1980, we only had about 7 or 8 days between the time that there was a first sign of activity to when an actual eruption happened. In 2004, started on I think a Friday afternoon, and the following Saturday, 8 days later, we had an eruption. So it goes very quickly, and emergency managers have just this time to make decisions, because look at this graph here. Any time scale you want, hours, days, weeks, months. And then on the y-axis, we have intensity of monitoring parameters. That's like how much the earthquakes are increasing in intensity or magnitude and how much deformation is happening. It's only a short decision window. They have to make decisions, and they don't know what's going to happen next. But let's look at some of the options for what might happen next. First, it might go directly to an eruption, at which they can play the heroes and say, oh, we can all say, oh, we knew this was going to happen, and it happened, thank you very much. But what usually happens is something different, and the volcano may go back, after acting up for a while, it can go back to sleep, or it can keep on keeping us on our toes for days, weeks, months, years, and then eventually go to an eruption. Or it can be active for a while and then go back to sleep without ever serving up an eruption, and boy, is that disheartening. We get called crying wolf when that happens. But we don't have any control, of course, and these are the options we have to be prepared for. Some of the work we do with scientists, USGS, and others, Dogami, is involved in this as well. I should mention they have an excellent program working with Mount Hood, especially at this point. But we've done a lot of work at Mount Rainier. It was our first work group. There we have the work group. We have a response, a coordination plan. They actually have evacuation route signage up, because in some areas there isn't going to be much warning. Those people live 30 miles from the mountain or so, and they're not getting a lot of radio or TV signals. They're not hearing any sirens. And so we tell them to just be ready to get to high ground. Get to high ground if there's any threat of a lahar. Know how you're going to get out of the lowlands. There's actually a lahar detection system that's been set up. Here's this little Iwo Jima type photo of, I think it's explorers and emergency managers and scientists setting up equipment. In the park, they have some evacuation routes and plans set up. There's long-term community outreach in the works, and we go out in the communities. The neighborhood emergency volunteers go out and talk to people, make sure that people know how to get out of the way. We've done a lot of things for educators as well. We also have a proclamation from Washington's Governor, Chris Gregoire. We have May declared as Volcano Awareness Month in Washington State, which gives us a platform to remind people that we live in an active volcanic range where we will have more eruptions, which will disrupt our lifestyles. Here's a little bit of the Lahar detection system buried in the ground. You can see what the sensor looks like, just a little geophone. Here is a school ground and a siren, an evacuation route to get people out of the valleys. We have more than 100,000 people living on old Lahar deposits in the Mount Rainier area. So we know that's a lot of people to get out of the way once we have additional activity. We work to get park exhibits up to snuff so that they're giving reliable information. We run a teacher workshop, and I actually brought along some little pamphlets today you can look at about our teacher workshop for middle school teachers that is happening July 18th through 22nd. And if you have interest, you can go to our website or you can see me afterwards. I can tell you more about it. It's a lot of fun. It's a week-long workshop where we're up at Mount Rainier National Park. Okay, so we also have a notification system. It's actually in black and white, gray and white, normal, advisory, watch, and warning. And then there is a separate aviation code for aircraft. And most of us use this gray one that shows what's actually happening on the ground. So, necessary preparations before the unrest begins. Know whether you live, work, or go to school or travel in a volcano hazard zone. Plan ahead. Have emergency supplies. Same thing you do for any other kind of emergency practically. Just be ready to be on your own for 72 hours or more. Make a plan with your family. Plan an evacuation route away from rivers and streams that may carry lahars. And if there's an eruption predicted, monitor the radio and TV for information. Follow the advice given by authorities. They have been thinking about this. So what can we expect at Cascade Volcanoes? We can expect periodic earthquake swarms, continued geothermal activity, eventual eruptions. It's not a matter of if, but when. We can expect a little bit of warning. It's not like we're going to have an eruption out of the ground with nobody knowing about it. Days to months or more in advance. Which will erupt next? It's always the $5,000 question. Nobody really knows. One could argue that Mount St Helens, because it's erupted so frequently, as recently as 2008, it's active now. It'll be the next one to erupt. But it could be any of these volcanoes which produce eruptions in Lahars next. Public notification. You can expect that we're going to get information out ASAP. And it's not in our favor. It's not in the favor of the scientists to keep anything hidden or whatever. Sometimes people say, well, there's something going on, but no one's telling me. Completely the contrary. We want you to know. And so we work with public officials to get the message out. So if you have further interest, contact emergency management authorities. Be prepared for every hazard. Get involved and celebrate your local volcano. Go visit Crater Lake. Go to the Bend area and visit all those wonderful small volcanoes over there. And the main thing is to recognize that when people become knowledgeable about natural processes, they can prepare for hazards, and then we can all live in greater safety and comfort, and I think that's what we all want in this beautiful corner of the world. Okay, thank you. We have questions?
Yeah, if we've got a couple questions. Before we do, I do want to thank our sponsors, Oregon Resource Corporation, also the USGS for allowing Carolyn to come down here as part of her job, also the college and the College Foundation. We have a couple questions. We'll take a few questions, and then those of you that have someplace to go will free you. And there's also a microphone over there if anybody's on that side.
Yeah, I was wondering if there's a chain reaction, like say Mount Hood erupts, does the cascade, cause, a chain reaction?
Oh, that's a very good question. So if we have an eruption at one volcano, does it mean that it might set something off or trigger an eruption in another volcano? That's a very good question. First of all, the answer is no. Each of these volcanic areas has its own magma chamber. And by magma chamber, I'm not talking about a soda bottle-like container underneath the volcano. I'm talking about a zone of molten and partially molten rock. There is not a connection between them. The only connection that there is that all of them have this subducting slab of oceanic rock diving beneath the continent. And about 100 miles inland, that's about where it starts to melt. And we have magma working its way to the surface. So no, we do not have a connection between the volcanoes. Now that said, it does seem that through history, if you look at the record, that when one volcano in a given area is active, we tend to have other volcanoes being active around the same time. And it's a big question, is why that happens. Do we have some change in the subduction? Is it triggered by large fractures that change through time? What's the reason? Why does it happen? But so you can see in the since our country was founded, we had 7 volcanoes erupt. So, okay.
I'm curious to know what happens if we have a major we have a major subduction earthquake. Let's say, for example, the husband right now. That's a lot of magma boiling up. Would that be likely to trigger that?
That's another good question. We have a trigger by a large earthquake, and we've always all wondered about that. And of course, we haven't been around with seismographs long enough to test that hypothesis. Back in 2001, when we had the Nisqually earthquake, 6.8, we wondered if that might trigger some activity at some of the volcanoes. And the principal activity we noticed was large snow avalanches at the Cascade Volcanoes. So a little bit north of here, we've been through, 1949 quake, a 1965, a 2001 quake. We haven't seen any change. Now, a subduction zone earthquake might be different. We'll note that we don't have enough information to know precisely when those volcanoes erupted around 1700, when the last big subduction zone earthquake happened. So we can't pinpoint it really and say that those eruptions were a result of it. That would have been Glacier Peak, principally, Mount Shasta. So we're watching, we're trying to figure it, but right now we don't see a connection. There's no smoking gun.
How does the offshore volcanic activity compare to the Cascade activity?
Okay, so what's the comparison between the offshore volcanoes, like the Axial volcano and those in the Cascades? If you look at volcanism around the world, you'll see that many, many more volcanoes happen under the surface of the ocean than on the continents. And there's a lot more, much more magma coming out, much more magma coming onto the surface of the ocean floor than there is onto the surface of the continents. So, yeah, they're happening a lot, and somewhere in the world on a spreading ridge, and they're big volcanoes, and they put out a lot of lava.
So, ladies and gentlemen, thank you for coming out tonight. I'm sure that Carolyn would be happy to stick around and answer your questions. And again, thank you. April 2nd, Andrew Fountain from Portland State talking about glacier retreat and sea level change. Have a pleasant weekend.
Thank you.